Welcome back to Control System Lectures. This video will focus on designing phase lag compensators using the root locus method. If you're watching my videos in the order of one of the playlists I've created, then you've probably just watched the video on designing a lead compensator using the root locus method, which is good because I'm going to continue from where I left off there. If you came to this video by another means, then you might want to first check out that other video. Now, I've already let on that the only difference between a phase lead and phase lag compensator is whether the zero or the pole is closer to the origin. The zero for phase lead or the pole for phase lag. Or another way of saying it is whether the time constant tau is larger in the numerator or the denominator. So you might be thinking, well, if the transfer function is practically the same, basically just a constant has been changed, then can't I use the exact same techniques for designing both lead and lag compensators? And yes, you absolutely can. I showed in the last video that the purpose of phase lead is to move the poles further into the left half plane. Here is a simple root locus of an uncompensated two-pole system. When we add a lead compensator to the system, we are effectively dragging those two yellow lines more to the left, where the pink lines are. We usually are doing this to make the system more stable, have a faster rise time, and so on. But in the root locus method, the bottom line is that we're trying to move the dominant poles to the location in the S-plane where our requirements want them. For example, we want to move the red poles to the green pole location with a lead compensator. You might refer to this as shaping the root locus plot, or actually moving the lines around on the plot. So if for some reason you want your dominant poles closer to the imaginary axis, then you can use a phase lag compensator to reshape the root locus like this in the exact same manner. Typically though, this isn't what you use a lag compensator for. Sure, there can be some advantages to moving the roots to the right, but I'll discuss them in the lag compensator with Bode plot video coming up next. In general, we use the lag compensator to address steady-state errors. For example, maybe you want to look at the error of a unit step input response at time equals to infinity. But the trick is to address these steady-state errors without changing the locations of the dominant poles, since they're already where you want them. As a consequence, you don't want to shape the root locus, at least not by very much. So you want to add the lag compensator in such a way that won't affect the shape of the root locus. And I'll explain how to do that. But first let me cover how the lag compensator reduces the steady-state error. If you've watched various videos on this topic or read various books, you'll notice that there are a lot of simple equations that can help you remember how to design a lag compensator. The problem for me, though, is that there are multiple different ways of approaching this problem, and I tend to get my helpful equations all mixed up, and in the end, I end up messing up the problem. Like, for example, does the a multiply across the entire numerator, or just the first s? And since I always forget these little helpful equations, I end up just starting from scratch and do it the long way. That way you're sure not to use the wrong equation, and you'll probably have a better understanding in the process. Let me draw a generic transfer function for a plant, g of s. But to make it easier in the future, I'm going to break this up into a numerator, gn, and a denominator, gd. I'll also add a lag compensator, s minus z over s minus p. Remember, the locations of the zeros and poles are negative since they're in the left half plane, so these will become z plus a real number. I'll feed back the output and compare it against a reference, u of s, to generate an error term, e of s. Now from my video on steady-state error, you know that the equation for ESS, or steady-state error, of a plant g of s is the limit as s approaches 0 of u of s over 1 plus g of s. And for a step input, u of s is just 1 over s. So this equation just becomes the denominator of g when s equals 0, divided by the denominator plus the numerator of g when s equals 0. So now when we add the lag compensator in the system, we can solve for the new steady-state error, I'll call it ESS of c, for the steady-state error of the compensated system. Now the total system is g of s times the lag compensator. And again, for a step input, u of s equals 1 over s, and the whole equation just becomes this. Notice that it is very similar to the uncompensated equation, but just with that extra pole and extra zero multiplied in. We can solve for the ratio of the zero to the pole and get this equation. Now ESSC is the desired steady-state error to a unit step input, and we can pick almost any value we want for this. We know the uncompensated plant G of S, and so now we can determine the ratio of the 0 to the pole for our lag compensator that will get us the steady-state error that we want. From this equation, though, it's easy to see that in order to reduce the steady-state error to 0, or basically have no steady-state error, the 0 to pole ratio would have to be infinite. That's why a lag compensator can only reduce the error and not eliminate it. If you want to eliminate it completely, you'll have to increase the system type, which means add a single pole at the origin. Let me show you a quick example with some arbitrary numbers. Let's say you have this plant, and you want to add a lag compensator to reduce the steady-state error to 0.1. Then the 0 to pole ratio needs to be 13.5 to 1. Or in other words, the 0 needs to be 13.5 times further away from the imaginary axis as the pole. But where do we place them? I mean, we can place the pole at minus 0.1 and the 0 at minus 1.35 and satisfy that ratio. But we could just as easily place the pole at minus 1 and the 0 at minus 13.5. There is an infinite number of possibilities still. To help us decide, we first need to remember that a point in the S-plane exists on the root locus if the sum of the angles from the real axis to the line that extends from the pole or 0 to that point equals 180 degrees. You add the angle if it's a pole you're measuring from, and you subtract it if it's a 0. So in this case, we know that this blue dot exists on the root locus if these two angles, theta 1 and theta 2, add to 180 degrees. So if I don't want to move the location of the locus very much when we add a lag compensator, then the angle of the added pole minus the angle of the added 0 need to be very, very close to 0. So we want to place the pole and 0 in such a way that they cancel each other out and there is no root locus shaping. If we place the lag compensator somewhere to the left of the dominant poles, then you can see graphically that the angle of the 0 is going to be much smaller than the angle of the pole. This is going to drag the dominant poles to the right, like I explained earlier on. However, if we move the lag compensator closer and closer to the imaginary line, but still keep the exact same ratio, then the angles for the pole and 0 become closer and closer together, and our condition is met. So the bottom line when you're using a lag compensator to reduce steady-state error is this. Maintain the 0 to pole ratio that you've calculated that will reduce your steady-state error to the amount that you want, and then place the pole and 0 as close to the imaginary axis as possible to reduce moving the dominant poles. But there is a limit to how far to the right you can move the compensator. And that's because if you're building this with resistors and capacitors, the closer to the imaginary axis you make this, the larger the components need to be, and eventually they become so large as to be impractical. So the rule of thumb is to place the 0 approximately 50 times closer to the imaginary axis as the closed-loop dominant pole. Of course, this is just a rule of thumb, so this is a place where you have a little bit of flexibility in the design. So for example, if you had your dominant poles at -1 at the real axis like we have here, then you'd want to place the 0 at -0.02 and then the pole at whatever the ratio is that is needed to meet your steady-state error. In the last video, we designed a lead compensator for a system in order to move the dominant poles from -1 and -3 to a complex set of poles at -3 and ±2 on the imaginary line. Now I've redrawn the complete closed-loop system and compensator here. And if we solve for the steady-state error to a unit step input for this system, we get approximately 0.3. That means that if we input a step of 1, then at time equals infinity, the output would only be 0.7. But let's say you have a requirement to have the steady-state error be reduced to 0.1. But you need to keep the dominant poles where they are in order to meet your performance requirements to an impulse input. So you go through the process of designing a lag compensator, and you find that the 0 to pole ratio needs to be around 3.8. And you know that the real portion of the closed-loop dominant pole is -3, since you designed it that way. So you find that you need to place the 0 at -0.06, and the pole 3.8 times closer than that at negative 0.016. So your lag compensator simply becomes S plus 0.06 divided by S plus 0.016. And you can place it in line with your lead compensator and your requirements will be met. Now I went ahead and plotted the step response and the impulse response for this system in Matlab and placed the plots here. You can see from the step response that the lead-only system produced a steady-state error of around 0.3, just like we calculated. And when we added the lag to it, it reduced that steady-state error to about 0.1. Although the settling time is pretty large, but we didn't have any settling time requirements for the step input. However, you'll notice that our impulse response is virtually unchanged, and that's because we didn't move the dominant poles very much, which is exactly what we wanted. Now in the next video, I'll show you the process of designing a lag compensator using the Bode plot method, which we will use to meet slightly different requirements. And if you have any questions or comments on this video, please leave them below and I'll try to answer them. And as always, thanks for watching.